L2? Yes? Question 1225. Say again? They're all in scientific notation? Really? Oh yeah. So what do you have, 1.7 times 10 to the negative 4? And then 2.3 times 10 to the negative 4. So all of those are times 10 to the negative 4. So you just got to move your decimal point 4 places to the left. So it's 0.00017, 0.00023, etc. Okay, so what we're supposed to do with this is we're supposed to make an estimate of E for a F of 4.8. So we can, if we look at these, and so I'm just going to put a couple things up here. For a 4 and 5.6, this is 0.00067. So those are your values right there. So 4.8 is about halfway between, right? And with this function here, the way you have it evaluated, this is linear. And because it's a linear function, you should be able to estimate that that value is going to be halfway between the 67 and the 93. What is that? 100 thousandths. So what's halfway between 67 and 93? Isn't it 0.8? Yeah, so then there's your estimate for an f-stop of 4.8. So let's see. And now it says, using your special camera, you set up an f-stop. You use your table to find two values close to the required exposure. So yeah, that'd be 4 and 5.6. That's if this is to the first power. Got to keep that in mind. Later, we do everything to the second power. So if we graph the order of pairs from the table on a coordinate grid and connect the points with a smooth curve, use the graph to estimate the required exposure. So is making a graph with these kinds of numbers, is that a challenge? It is. Okay, so I'm just going to sketch one. And that I'm going to use my data from here, where my L1 is going to be F. This is going to be list 1. This is going to be exposure, which comes from list 2. And your f-stops go from 1 to 5.6. So I would just say 1, 2, 3, 4, 5, 6. And 0, which doesn't exist. But then you have these kinds of values that are going to go with. So the smallest that you're going to have that goes with 0 is 0.00017. So, and then the biggest, so we have to go from, when this is a 1, 0.00017, and then we have to go all the way up to this value. So it goes from 17 to 93 hundred thousandths. So I guess what I would do is I would just say that this has got to go from 0 to just a little bit bigger number than that. This is hard. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's how I'm going to get this done. And I'm going to say that this, if this is 10, that's going to be 0.001, 001. And then this is going to be 0.0009, 0.0008, 7, 6, 5, That just worked. And what I did is I thought of this point up here as am I doing this right? Yeah, it works. I've got the right number of place values. Okay, so now when you take this data and you put it on there, or you just graph it on your graphing calculator. And then if you're going to graph it on the graphing calculator, your y's need to go from 0 to that number. And your x's need to go from 0 to 6. So why don't you go to your window and set that up? X minimum of 0 and a maximum of 6. And then you could have the scale of 1. And then the y minimum of 0 and the y maximum is going to be this value, 0.001. And then your scale is going to be 0.0001. 0.0001. Make sure you have stat plot turned on. And graph the thing. And you'll see the points. They should line up beautifully. Good with that. So how far are you with it? Have you set your window? Do you have the data in L1 and L2? Do you have all of those? Hit enter. No, you don't. Here. Because I want to keep this moving forward and go back and help you with entering data in the future. But when you hit second, xt theta, second xt theta. And then what we receive and hit enter. Okay, and then scroll down to number 3 and hit enter. And then hit enter again and second click. Okay, now go to your lists. Stat, edit. Okay, there's got the numbers. And now go to window. And set everything just like that one. How are you two doing? You don't have L1 and L2 in there? These are going to be the L1s right here. L1, 1 by 4. So hold on, we're L2, good. Go over. Okay, over. There you go. Yeah. Okay, that's going to be parentheses 1,6,000. You guys should have stopped me back then and said, hey, I can't get it entered into the lists. Otherwise, you know I'm a runaway train. I won't stop. You have stuff in? Okay. You don't have to worry about it. These numbers down here. Just down to the scale. This is scale. Good. Okay, I want you to go back to stat and enter for edit. So what we did over here, what I did for that, is we took these numbers, we put them to list 1. We entered them in. And then in order to get all of that, go up to L2 and highlight it. Hit clear. Clear, and enter. Okay, now go back up to L2 again. Okay, so what we did is we put this equation in. And this is going to be the L2, so all we did is we typed equals parentheses. Now let's start with your parentheses. Nope, not down there, up, yep. There you go, because that'll do it for the entire list. So 1 divided by 6,000, parentheses, times the F values, which are in L1, times, and the second number 1 is L1. Okay, so you know how you got that L2? That's all good? Okay. Okay, so what you'll do is go just gonna do parentheses, now divided by 6,000. Parentheses again, and then L1, and hit enter. There it is. Those are the correct values. 0.0001, 0.002, 0.003. So now you get to set up graphing that. Okay, so for all of you to set this up graphing it, you do second stat plot. And you make sure plot number 1 is turned on. Okay, parentheses. Divided by 6,000. 6,000, there you go. And then second L1. Oh, you don't, no, okay. Okay, just overwrite that. Second, and then number 1 is on. Now hit enter. I just calculated everything for you. Okay, so go to second, stat plot. And hit enter so you can turn number 1 on. You have number 1 turned on? Yeah, and then make sure the X list is L1 and the Y list is L2. So you read down, X list is L1, Y list is L2. And the type of graph is the first one, which is scatter plot. And as soon as you have that, just go to your window. Do you have your window set? Yes, that's set. Now you just hit graph. There. There. Yes? Okay. So we all have a line from that function. So this is a linear function. It goes something like that. This is going to be this function. Please, you guys, when I'm asking you to do stuff on your graphing calculators and you're not getting it on with me, onto the calculator, stop me right away. Just, you know, some of you are doing it and I just think, well, everyone's got it. But if you don't, you know, squeaky wheel gets the grease. If you don't say anything, I'm just going to keep piling away. So there is this, you know, you look at it, it's a linear function. So then from the graph, you ought to be able to say, oh, well, if I looked here at 4.8 and I went up, and if you look at your graph, if you move over, you look at your tick marks on the bottom, your tick marks are set up like this. 1, 2, 3, 4, almost to 5, you go all the way up, you go all the way across. It's a little harder to see, but that's okay. You can see that it's reasonable. And the table, maybe the table works really good. Seeing a table of these values is a real challenge on the graphing calculator. If you had entered a function, if you just go to second table now, you won't have anything in there. And the reason that you won't is because you did not enter a function into y equals. So the table just comes from y equals. When you make scatter plots like this, the only table that you have is the list 1 and the list 2. Now, go back to your lists. Go back to where you have L1, L2, and L3. The problem said that you might have this as the relationship. We don't know. Well, I don't know whether we do or we don't, but it's one or the other. We'll figure this out as we go. So what we can do here, just like in L2 we did the 1/6000th of f, we can do 1/6000th of f squared by doing parentheses 1/6000th times L1 raised to the second power. So put that in for L3. Well, then you have something that you did wrong. Let's see, so I entered 6,000 parentheses, list 1. Well, you're pulling list 2. Yeah, or your X. Just, yeah. The second L1 raised to the second power. Are you guys getting it into? Yeah? Is your first one 1.7 times 10 to the -4? Yeah. Okay. You gotta go to lists, which is have those values, look at them all, are they gonna graph okay for you? Are they gonna fit on the graph that you have? No, they're not, because like 0.0052 is like, that's gonna be 5 times as big as this. 0052 will not fit on the graph. So what you need to do now is you need to change on your window, you need to change the upper limit so that it will accompany that 0052. I don't know, I would say make it 005 or 006.006. So the Y max has got to become 0.006, which is really going to change the way this first function looked. But that's okay, because you know that it's linear. So do you have L3 filled in?
It says error.
Okay. Speak up. So quit that and go back to your lists. Stat, edit. Okay, parentheses. 1 divided by 6,000. I suggest you keep the thing not in your hand like a phone. So I set it on the table, see? Because these keys aren't designed to be done by our thumbs. Okay, then you do L1, which is second, yep, and then raise to the second power. Now you can enter, there you go. Now change your window. You guys all have your window changed so the Y max is 0.006?
Yeah, but I still don't see anything.
You don't see anything?
Like, it's the same as it was, just with a different scale.
Right, yep, that's good. Okay, now what you have to do is you have to pick a second set of data to be graphed. So we're gonna put one graph on top of the other. Right now, all your calculator is being told to do is take list 1 and list 2. Now we need to take list 1 and list 3. And that's gonna become a second stat plot. So go to second stat plot, go to plot number 2, which is probably gonna be a red one unless we've changed the color. Turn it on, and where it says X list and Y list, make sure it's pulling from list 1 and list 3.
I don't have the option to select what's one of those 3.
Then you are not where you need to be. Let's see what you got. Okay, you're not there. That's Y equals.
Well, because that's
Oh.
how I got this here, was by
Yeah.
doing that.
Yeah, well, what you have to do is you up, then you go over, and then you hit enter. That just turns it on and off, so you gotta do second stat plot too. Okay, so now go down to 2. It's turned on, but hit enter. And now change it to L1 and 3. There you go. Now when you graph it, it's there. Is it there now?
Yeah.
So you have 1 and 3? There. Now you can see one is linear and the other is exponential. Oh, your Y minimum is 0. Yeah, your window is different.
Oh, I changed my mind.
Yeah. It should be, here's what I've got. Your Y minimum needs to be 0, the max needs to be 0.006.
Yeah, but what's wrong with that?
Well, don't even, oh, your scale, 0.0001. Now grab, there you go. Yes. You have it? All right. So from that, if this is the function, you're gonna have a much different estimate for 4.8, aren't you? What's the easiest way to find your estimate for 4.8 using the squared function? How would you go about it? Do you want to use the graph or you want to use the table? The table, I think the table's better, so you just go back to your list. And if you look down halfway between 4 and 5.6 is where you'd be. But the problem with this is that it's an exponential change. So when we look at this, it might be that the graph is better. So this is what we have on the graph. I think that the graph is probably easier to use, in all honesty, just because, horizontally on your graph, you move halfway. But vertically, this thing, if this ends up being 0.006, it comes up like this. And if this is 4, and this is 5.6, for example, you need 4.8, which is right here. But when we have an exponential function, it doesn't always end up, this isn't a very pretty graph, but it doesn't always end up being halfway between these 2 points vertically. It's usually a little bit further along on the line because of how things, when they change, you're taking this value on the horizontal axis and you're squaring it. When you multiply it by itself, it's going to make a steeper curve. So if you can see that with the graph, that's a good thing. Let me take you a step beyond. Let's do this. Go to y equals. And y sub 1 should be blue and y sub 2 should be red, yes? Okay, so in y sub 1, let's do this. Parentheses 1 divided by 6,000 times now x. And then in y sub 2, do the other equation. 1 divided by 6,000 x to the second power. Now what you're going to do is you're going to shoot a line over your data. When you hit graph, you have a blue line going through your blue points and you have a red line going through your red points. Did that happen? Okay, so now when you look at that, here's how you go about estimating the value for f-stop of 4.8. Go to the top and see the trace button. Hit trace. And you'll see you have a cursor blinking. Use your arrows to move to the right just a little bit, but then move up. Use the arrow to jump up and get on your red line. And then use your arrow to move yourself over. And if you look on the bottom, the x values are going to be there. And you can get it to come pretty close to 4.8 when you're tracing. So you're going to see an x and a y value on the very bottom of your screen as you trace. Okay, so right now you're not tracing. What happened? Just move arrow over. Okay, up. Yeah, now move it back. Okay, go up again. And now move it back. And go up again. And again. Again. Go down. That was over. Here's what I want to do. Maybe a second. Graph. Trace. There it is. Now it's in between. There you go. So now you can look down here and get it close to 4.8. Are you doing okay with tracing? Or is it just jumping?
It's jumping.
Oh, it's not bad. You're sliding along the line. It's not going to hit exactly 4.8, but it's going to get really, really close. On the blue line it was jumping? Yeah. So how are you doing with tracing? Is it slide? Yeah, there you go. You just slide along. You can find about 4.8. Come on over here. You were and you're sliding, so you found it? Okay. Yes? All right. So there, that was a lot of time. But I hope that you can internalize a little bit of what you did with this. Because the exact set of operations and such is something that you can do, you can use over and over. And you can use it to solve, once you get smooth on the calculator, you can use it to solve equations and find answers to problems very, very quickly. So here, ACT and SAT reality. Joan spent a lot of time this summer working with Haley on her ACT and SAT skills. If is Haley's got aspirations to be in the Air Force or Naval Academy, which is a pretty competitive thing to do. So she wanted to raise her scores as high as she could, and she put in huge amounts of time. And in what we figured out, between Joan and I and Haley, what we figured out was her biggest problem was not in understanding how to do the math. But her biggest problem was getting it done fast. And because these tests are time tests. You guys are, you're used to coming through middle school where you took math. And it's like, you want to take 6 weeks getting your math test done? Some people would do it. They just take forever, literally hours and hours and hours on a 50-question test. And then we take peaks when you guys are taking those standardized tests for the state in the spring years. I can't remember what Washington calls theirs, but standardized testing that everyone sits down, it's just the gruel. And there's no time limit, right? All of a sudden, here comes ACT and SAT. You have 50 minutes to complete this test. And you open it up and you go, man, there's 60 problems. Holy crap, what am I going to do now? And students here that I talked to, many students said they would get down to the last 3 or 4 minutes of the test, and they would have 15 problems to go. So what do? Guess. You're nodding your head. You've heard this before. And you guys are going to do PSAT on the 14th, aren't you? Time.
And some of us are gonna take the actual SAT.
Yeah. Which you should. You're juniors. You should be taking SAT and ACT now. Like spring of this year. Get this class behind you. And then take it. But you need to learn time management. You can't sit on a problem and sit there and dwell and dwell and dwell on it, because it's just going to bury you for the rest of the test. And then you'll have all these other problems that you'll get to, but you won't have enough time to finish them. And you'll be saying to yourself, well, geez, I know what to do, now I just don't have the time. So you can't get hung up on one problem. If you can't do it, if you don't know how to do it, skip it. Come back later. You need to discipline yourself to do that. And you need to do that when you're taking my tests also. When you get to one you can't do, screw it, just move on. And if you look through the whole test with my tests, find something that you know you can do it quickly and get it done. And then come back to the other stuff. How do you get so that you have an advantage? You learn how to use this graphing calculator. Because this thing can do so much busy work for you if you let it. So the lists are important for creating graphs, for being able to take a whole bunch of input values and get the answers when you're using the same function for each of them. Those are the 2 big tools with this right now. The tracing function on a line to estimate, huge. Now that you have those functions in this one, or I'm sorry, in y equals 1, y equals sub 2, go to your table, do second table, and take a look. Now you have all your y sub 1s and your y sub 2s in blue and in red. So now you got all kinds of numbers. You want to find 4.8 on each of these graphs? Here's what we do. If you look, your x values probably change by 1s, don't they?
Yeah.
Is that right? So you need to change that. So that's called second table setting, TBL-SET. That's the window button, second table set. In the delta TBL, change that to like 0.2. And then the starting number, start yourself at like 4. And then go back to your table, and you can go, 0.2. What did I do? I should have find 0.02. Right out loud. Do the 0.2. 0.2. Go back to your table, and then look, you got 4.2, 4.4, 4.6, 4.8. And now you can compare the exact values that come from each function. Now granted, question number 12 wanted you to do some estimating, but I want to show you how to use these things. we don't spend $140 a piece and have as many as we have, so we can just say, well, these are really pretty and cool. This is an extremely powerful tool. It's just like your computer, except you get to use it on tests. Are you all able to find the table set? You get it? You got that? All right. So that's basically question 12. More, or should we go on? Let's graph hyperbolas. Okay, so 2-6. If you're trying to get something done, the FST and the calculus students, you talk to them about how to do something on the graphing calculator and they can help you. The FST, the calculus students, Joan and myself. Those are your go-tos. And those guys, the seniors are pretty good with these things. So, graph of these inverse functions. They write it as y equals k over x, y. K over x and x squared. So with an inverse function, the idea behind an inverse function is that as your input goes up, your output goes down. Or think of it vice versa. If as your input goes down, your output goes up. So the values go in opposite directions. So if you look at a table of values, as one column is increasing, the other column is going to be decreasing with these types of functions here. So if we think about that graphically, let's just do this. If I just sketch something like here. If I start at a particular y and x value, if we look at this, when x is really, really small, if we take a constant and we divide it by x, by a very tiny number, what's y going to be like? Is it going to be big or is it going to be small? Take, for example, 1. 1 divided by 0.0000. This is really, really tiny number. What kind of answer is this going to be? A large number or a small number? That's going to be a really big number. So if I took k as 1 and I divide it by a very small x value, so in other words, an x value that's way over here, you're going to have a very high y value. And then as x gets bigger, eventually, you're going to have smaller and smaller values. And then, eventually, 1 divided by 1 is going to be 1. 1 and 1 is going to be 1. If I had y is equal to 1 over x. So this line is going to come down like this. And then, as we divide by larger and larger numbers, 1 divided by 4 is going to be a small number. 1 divided by 100 is going to be even smaller. So as we move further out the x-axis, the values get smaller and smaller. That's not a real pretty line. If I make it a little bit nicer, this is what the general shape of this graph is going to look like. It's going to be like this. It's going to curve down, and it's going to flatten out. Is it ever going to get to 0? Like if I took 1 divided by 1,000,000, large or small number? Very small. What if I did divided by a billion, or a trillion, or a quadrillion. It's gonna get smaller and smaller. Will it ever make it to zero? Never will. So this line is gonna flatten out, it's gonna get closer and closer to the x-axis, but it's never gonna make it. And just like over here, if we divide by smaller and smaller numbers, it's gonna become a larger output value, but it's never, ever going to make it to any endpoint. It's just gonna keep getting bigger and bigger. Now, here's a question for you. What about this? This is x is equal to 0, the y-axis. Can we put 0 into this denominator and divide? Because division by 0 is undefined. So we're never going to be able to take a k value, like if I use 1 or whatever it is, and divide by 0. So that means the line will never cross the y-axis. It's just going to get closer and closer and closer, and it will stop at 0. It will not exist. So let's go a little further. Let's say that x is now a negative number. And let's think about this over here. So let's just do y divided by negative 1. Which one divided by negative 1? Negative 1. So if that's my x, this is my output. So when x is negative, y is negative. If I had 1 divided by negative 10, that's equal to, negative 1/10. No, let's just keep going. Y divided by any number negative will be equal to a negative answer. So this shape is on this side of the y-axis, but it's down in quadrant number 3. So this is called a hyperbola. And that's the graph of y equals k over x. So the domain and the range. The domain is complicated, but we can write it in a relatively straightforward, simple way. The domain would be all of the inputs that are reasonable. And we can use any value of x, can't we? Except for 0. So the way we would write this is we would write all real numbers. Can I use this abbreviation again? Is that all right? Do you know this one? Okay. However, x may not be equal to 0. Very important. Lots of test questions will try to hang you up by having something in the denominator that becomes 0. And when that happens, there's no solution. So to keep that in the back of your mind, especially when you jump into PSAT next week. Whenever you see any possibility of a 0 coming up as the denominator after it's simplified, no solution. So now the range is everything except 0 again. There's no way to take a real number and divide it by another real number and get 0, unless you're starting with 0. But see, k can't be 0 in these functions, so we're restricted. This is going to be all real numbers, and y is not equal to 0. These are your outputs. Okay, now, go back to the graph. Because these lines, they flatten out and they never touch the x-axis on both sides, we say that that x-axis is an asymptote. At the same time, vertical y-axis is a line that is never touched by these curves. It approaches, it gets really, really close, but it doesn't touch. So in this case, the y-axis is also an asymptote. So asymptotes are vertical and they're horizontal. And so an asymptote is a line that a curve approaches but never touches. And when we say a curve, we're talking about the function curve. And these kinds of functions have asymptotes. So I'm going to do a little bit of writing up here, get rid of some of this. And we're going to say what the vertical and the horizontal are. Funny story. When I took Calc 1, I took it from a Japanese guy who had a very, very strong Japanese accent. He was hard to understand. His English was real tough to understand. And he was talking about asymptotes. And he called asymptotes asymptotes. And I didn't have it figured out for weeks and weeks and weeks that he was actually pronouncing asymptote as with a different pronunciation, asymptote. So several years later, I'm sitting in a completely different town, different university on the other side of the state of Wisconsin, in a graduate class, and I sit down at a table next to another teacher, a young lady from Minneapolis, and we ended up being partners working together on projects, and I was talking to her, and the professor that I had that said asymptote, his name was Gunji. He was this Japanese guy who used to stand in front of the room like this. And when the bell would ring, while the bell was ringing with chalk in his hand, he would turn and go nonstop for an hour and a half straight, lecturing, doing calc on the board for an hour and a half straight. Maybe it was an hour and 40-minute class. I think it's some crazy length class. And he would go, and he would go, and he would go. And he'd erase his way back, and then he would go and go, and he'd fill these boards nonstop. And then he would turn like this, he would set the chalk down, he would turn, he would stand and he would look at the class, and literally when he would do that, the bell would ring for class to be over. And he would pick up his papers and he'd walk out the door, and everybody's sitting in class scribbling away as fast as they possibly could to keep going. He was insane. He's the same guy that when he said, you have whatever amount of time, something like an hour and a half for the examination, at this time you must turn in your examinations. And time was up. The bell rang. He said, turn in your examinations. Everyone that still had theirs got up, walked up, set them down, except for this one girl in the middle of the room. She's fervently just trying to finish out this one problem and write in her answer and everything. And Gunji grabs all this stuff and he walks out the door and he goes over to the elevator. It's a big, huge building. Goes to the elevator, gets in the elevator, turns around, the door is open, and she comes running up to him at the elevator. Dr. Gunji, my examination. He said, I told you to turn in your examinations. You didn't. The elevator closes, and up he goes to his office, and she stood there crying. Never saw her again. She dropped the class. He wouldn't take her test. Gunji, asymptote. He was rough. So here I am. I'm sitting in River Falls, Wisconsin, with this woman from Minneapolis. And we're talking, and I slipped, and I said asymptote instead of asymptote. And she stops, and she jerks her head, and she said, you had Gunji at Madison, didn't you? So then we had stories about Gunji. And he was good, but strict. He is by far the most strict professor I've ever had. He was unreal. So the vertical asymptote is a vertical line. What's the equation of the y-axis? X equals 0. What's the equation of the x-axis? Y equals 0. You will find that we can move hyperbolas up and down and left and right. We can make them shift position, and then the asymptotes will change. But for now, it's just the y-axis and the x-axis. Okay, so let's go to your graphing calculator. Y equals graph 10 over x squared. Y equals 10 over x squared. So when you do this, I think you can get away with just going into y equals, clearing things. I would clear them so you don't have these other things. You just, it's going to be x divided, 10 divided by x raised to the second power. But then when we do it, we want to graph it in a standard window, and your window's all goofed up, isn't it? But we don't have to go back and change everything. We can just hit zoom, once you have your equation in, and hit number 6 for Z standard, and it will graph it on the standard window. Now you might still have your points from list 1 and list 2. But that won't do too much. So you got something? So back with you, y equals 10 divided by x squared. Okay, now do window. Excuse me, zoom. Zoom on number 6. Okay, probably because your lists are interfering. Sometimes that happens. So go to second stat plot. If you go to second stat plot, you can turn off those lists. Leave them in there. You might need them for your homework. And then just go hit second stat plot again, scroll down to list number 2, or plot number 2. And then if you go to your graph, how does it happen? Yeah. Can I look? So yeah, it says to check your plots. So you have number 1 on the second step plot. Turn that off. Yeah. Hit enter. And then scroll over. And then enter. And now just hit graph. Okay. You have yours graph? Yours graph? Yes? So because of the squaring, even if x is negative, the output becomes positive. So if we were to sketch this thing, it's going to look like this. And here's your y and here's your x. So no matter when you have a negative x value, you have a negative multiplied by a negative and your output becomes positive again. What do you think would happen if we made that negative? You'd flip it down to the bottom, exactly, and then you'd have 2 down here. So let's look at this. What are the asymptotes? Yeah, y-axis and the x-axis are your vertical and your horizontal asymptotes. All right, now let's go to y equals. And under y sub 2, do 24 divided by x squared. And graph those right on top of one another. Got it? How are they different? Yeah, it sits above it, doesn't it? Yeah, because your numerator is larger, your outputs end up being a little bit different. So, you have enough to go through this homework. I know it was a long story, but hopefully that what we did is gonna help you in the long run and make things more efficient as we go. Do you want me to tell you what the problems are? It's an ugly list. You're probably better off getting them online. I'll write them, in case you wanna write them. You got 2 days with this. Quiz Friday on lessons 4, 5, and 6. I guess this will be the last part of what's on the quiz. Have a nice day. Have a nice couple of days.